So, hello everyone, how are you? I hope that you must be enjoying the lecture series. So, in the last lecture, I was talking about how to draw the various free body diagrams along with the shear force and bending moment diagram. Also, I just related my diagrams with the mathematical equation and I drew various conclusions where you could find what are the various relation between what we are writing and what we are drawing the diagram geometrically. Means what we were saying was the mathematical interpretation with the help of diagram. Means first you have to solve the mathematics and accordingly you can draw the curve or the diagrams what we were speaking. Now I ended with a point that was a point of contraflexure. So just I want to remind it again as this is a very important point, and in GATE paper you can see a various questions like this, that they will be giving you the loading diagram in a beam and they will be asking you to find what are the number of contraflexure points or what are the number of points. They will not ask you directly that what are the number of points where the bending moment diagram is changing its sign. So whenever this term contraflexure is given, the first thing that must strike in your mind is this means nothing but the points where bending moment is changing its sign. So what do I mean is that whenever the positive bending moment is going to be negative, or from negative it is becoming positive, in that case you are seeing a change in the bending moment diagram, and this is nothing but the point of contraflexure. So I have just taken an arbitrary, I will show you how I have drawn the diagram like this. We will come to see later. Just at this point of time, you take it as this is the bending moment diagram of this loaded beam, and you can see here that at this point the bending moment is 0 and it is changing sign. So again, a very important point to note here is it is not that the bending moment is 0, we are calling it point of contraflexure, but as the bending moment is changing sign from positive to negative, that's why we are telling it as a point of contraflexure. In the last lecture, I gave you example also. Suppose this is my reference line and I am getting a bending moment something like this. Just it is touching the reference line and again it is coming down. So earlier it was negative and now also it is negative. Though this point represents that the bending moment is 0, but we will not call this point as point of contraflexure. So this point will be known as point of inflection point. So this is nothing but a point of inflection. So you can take it in this way that point of inflection is a broad term and point of contraflexure is a special category of point of inflection where you will observe that bending moment, apart from being 0 at that point, it is changing its sign. So why is this point important? This point is very much important because of the fact that whenever I draw the elastic curve, there is one more term that is generally used is elastic curve. So what is this elastic curve? Elastic curve is nothing but the line representation of the beam which will be seen after being deflected. What I mean to say, after you have applied the load in the beam will deflect in a certain pattern, and that pattern is given by the elastic curve. So this is the elastic curve. This is the elastic curve of this beam. So this elastic line means this line is representing how this beam has deflected after the application of the load. So from this diagram, this deflected shape of the beam has been shown here. It is written here also. You can note it down. And this is shown like this. And up to point B, there is a concavity upwards and suddenly there is a convexity. Means what I mean to say that from this C point, the nature of curve is changing from C point itself. So that's why it is of very much significance that whenever the nature of the elastic curve from convexity to concavity or from concavity to convexity, it is changing, it means that that point is very much vital in our design purpose, but because that point will be more prone to damage. So here there is a write-up also on this, that in this diagram we have noticed that for the beam as loaded as shown in the figure, the bending moment is partly positive and partly negative. So that I was only explaining that this part, this red shaded part is positive and this blue region is negative. So as the bending moment is changing sign from positive to negative, then we can conclude that it is a point of contraflexure. So point of contraflexure is the point where bending moment is changing its sign. So in the deflected shape of the beam, that is nothing but the elastic line shown below, the bending moment diagram in the left hand side of the beam is sagging, while right hand side of the beam is hogging. As I already told you that the positive bending moment will represent sagging and negative bending moment will represent hogging. So from sagging to hogging or from hogging to sagging, if the beam is changing or the bending moment diagram of the beam is changing in that manner, then we will conclude that that point itself is the point of contraflexure. Don't get confused. Whenever you will see that the bending moment are zero at several points, then first criteria must be, you must check whether the bending moment is zero, and the second benchmark is that you have to see whether the bending moment is changing its sign from positive to negative or negative to positive, or in a way sagging to hogging or hogging to sagging. So that will be the indication of the point of contraflexure. So now the point C shown in the beam where the curvature changes. So I was speaking about concavity and convexity. It is nothing but a part of curvature itself. So it is from sagging to hogging is a point of contraflexure. It is a point of contraflexure. So I think that you will not be getting any confusion in future in point of contraflexure. Now moving on to our next topic, that is, I have just theoretically whatever I explained you, I have given a note here. Whatever I spoke earlier, that what will be the slope of that diagram, what the slope of bending moment diagram that you will be getting, then what will be the slope of the shear force diagram that you will be getting here, I have represented it in a note form, and you can always write it or remember it. So here, the first relationship is, this W is nothing but, W is loading intensity. So this loading intensity will be of much significance when we will be dealing with uniformly distributed load and uniformly varying load. But for the time being, you take it into consideration that this loading intensity is nothing but the slope of shear force diagram. So what this dV by dx is representing? This is representing the slope of shear force diagram. This is the slope of shear force diagram. So why there is a negative sign here? There is a negative sign here because you will see that the loading intensity that we will always be directed in the downward direction. Suppose I take an example here. This is my beam and this is my uniformly distributed load, which is being supported at the two ends A and B. So this load is always acting in the downward direction. So whenever we are to find the loading intensity from the shear force diagram, so what we will do is, we will find the slope of the shear force diagram and we will put a negative sign there, then we will be getting the loading intensity. So the slope of shear force diagram is negative of the value of applied loading or the loading intensity. This is, mind you, a very important relation that you will be seeing in the later part, that directly from the, if you are asked to do the reverse calculation, that is if you are asked to calculate the loading diagram from the shear force diagram, then this relation will be very important. Now, moving on to the next relationship that I continuously went on speaking, that the slope of bending moment diagram, this M is representing moment. So this M is moment and dx is the elementary length. So whenever you have a particular bending moment diagram, from that diagram, if you find the slope, then you will be getting the shear force. So directly the slope of the moment curve, that is the bending moment diagram, is nothing but the shear force. And so it is nothing but the shear force. So remember the pattern which is being followed. The loading intensity we are getting from the slope of shear force diagram. The shear force that we are getting is from the slope of bending moment diagram. So it is just a sequence that which is being followed here. So these two relation, I am writing it here again, that loading intensity you are getting from minus of the derivative of shear force, and shear force you are getting by the derivative of bending moment with respect to x. X is the, dx is the elementary change in the length. Means whenever you are taking a slope at a point, suppose I am drawing an arbitrary curve like this. So if I want to find a slope here, so what we do mathematically, what we do is we just draw a tangent to this line. So suppose this is my tangent, and it is making theta. So what is the slope at this point defined as? It is dy by dx, which is nothing but the tan theta. The slope is always defined at a point only. It is not defined at a region. And whenever the slope is constant, like in the case of a straight line, then we can say that the slope is remaining constant, or the parameter by which we are getting from the slope is constant. Like if the slope of the bending moment curve is constant, like if the bending moment diagram is a straight line, suppose it is like this, so the slope is always constant, theta is constant at each and every point, then we can conclude from that our shear force is remaining constant between the 2 points. So this was a very important relationship. Moving on to the next. Now, this is the combined form of the equation. So how I am getting this equation, I will let you know. Just see carefully here that our loading intensity was defined as minus dv by dx. Suppose this is my equation number 1. And my shear force was defined as slope of bending moment diagram. So now, if I put this value of v here, I substitute the expression of v into equation 1. This is my equation 2. And if I substitute the expression of v, then I will be getting is w is equal to d by dx with a minus sign, and it is dm by dx. So mathematically, you can rearrange this expression and you can write it as minus d2m by dx2. So from calculus directly, if we double differentiate the moment, then we will be getting the loading intensity. So this equation will be very helpful to you whenever a question is given like this. I am showing you a question like, I have given you a question that my moment equation is varying in a way x to the 3x to the power cube plus 4x square minus 2. Suppose I have given this expression. And now I tell you to find what is the loading intensity in the beam at x equal to some position. Suppose this is my total beam and I tell you to find, and this is starting from x equal to 0, I tell you to find what is the intensity as x equal to L1 suppose. So at x equal to L1, what you have to do is, you have to differentiate this expression twice. So what will be the first differentiation that you will be getting is, it will be 3 into x square plus 4 into 2 into x, and the differentiation of constant is 0. So it will be dm by dx, which you will be getting is 9x square plus 8x. Now our purpose is not solved because we are asked to find the loading intensity. Now to find this loading intensity, again you have to differentiate this expression once more. So it will be d2m by dx2 is nothing but 9 into 2 into x plus 8, which comes out to be 18x plus 8. So whatever the distance it is given to find out, suppose x equal to L1, so put the value of x here, you will be getting the negative of that of will be the loading intensity. Don't forget to put here the negative sign because it has significance, as we are assuming that load is always acting in the downward direction here. So the negative of that will be our loading intensity by putting the value of x here. So this formula has got a very good significance. Now I just want to revisit into my slides that this was the expression for the shear force, where V is shear force. So this is W equal to minus dV by dx. You must remember this expression always. The second one is shear force is nothing but the slope of bending moment diagram, which is nothing but V equal to dm by dx. And the next one is the combined equation, that is you can get the loading intensity directly by differentiating the moment equation twice. So this was the very important part, friends, because whenever you get stuck in your physical interpretation, then only mathematics will be helping you out to confirm whether you have assumed the answer or you have calculated it correctly or not. So it is the mathematics only that will guarantee the accuracy of your results of bending moment diagram and shear force diagram. So in due course, I will tell you how we are using this tool in the purpose of solving the problems. So this is the reverse of what we have in the last lecture, means in the last slides, we were seeing that the differential of a quantity, like the differential of shear force was giving you the intensity and differential of the moment was giving you the shear force. In reverse manner, if you calculate the area of the shear force, it will be giving you the bending moment, and if you calculate the area of the loading intensity, then it will be giving you the shear force. It is reverse, friend. Whenever you are going from lower side to higher side, that is from the loading diagram to bending moment diagram, what you have to do is you have to go on finding the area, and whenever you are coming from top to bottom, that is from bending moment diagram to the loading diagram, then you have to differentiate the results in each steps. So now this mathematical term W equal to minus dV by dx. So what is the mathematical meaning is, you take dx this side, so it becomes W dx equal to minus of dV. Now I take minus to this side, so minus W dx is nothing but d into V, and I will integrate both sides. So what does integration means? Integration is the tool by which we find the area between the 2 points. Suppose I just want to recall you the concept of the calculus that we used to study here. Like suppose this is my x-axis and this is my y-axis, and I have taken an arbitrary function. Suppose this is my fx. This is my fx. This is my arbitrary function fx. So whenever you were asked to find out the area of this curve between A and point B, suppose this is my x equal to A and this is x equal to B. So we have to find the area of this shaded region. So what we did was, we took an element at a distance x of dx thickness, and we wrote that fx dx is nothing but the area of this diagram between A and B. So this is the area. So this is the area of the diagram. So this area will give me the shear force. The area W dx will give me the shear force. So V is nothing but V naught, that is the initial limit. This is the initial limit. Here it was A plus the negative of the area of the loading diagram. So why this negative? Because the negative sign was already present. So it will represent the area of the loading diagram. So in a gist, I can write it here as shear force is equal to area of the loading diagram. So it is nothing but the area of the loading diagram. So now moving on to the next is, as I was speaking about how I converted the bending moment to shear force by calculating the slope of the bending moment, we were getting the shear force. So in the reverse manner, what will happen is, if I calculate the area of the shear force, then we will be getting the bending moment. So here in the expression, you are familiar now with this expression very much, as it has been used several times. So again what we will do is, we will take dx this side. So it will be v dx integration is equal to dm integration. So it is nothing but, if this is my arbitrary curve in x and y direction, and this is my arbitrary shear force diagram, and if I am asked to find the bending moment between these 2 points, so what we will directly find the integral of this function. Suppose this my bending moment function is defined as x, so it will be nothing, the shear force, it's the shear force defined as the function v. So if suppose this is my function v, so it will be v into dx will give me the area, and this area will be nothing but the moment. So moment will be the initial limit from which we are finding, that is m naught to and plus the area under the shear force diagram. So the area under the shear force diagram is basically giving you the bending moment. So these two results, that is the slope, how we are utilizing the slope to find our shear force and loading intensity, and again we are utilizing the diagrams of loading intensity and shear force to calculate the bending moment. Now I just want to highlight one question here that keeps on coming, that why we are required to learn all these things. The simple reason is, friends, that sometimes what in gate paper you will see that you are given a shear force diagram. Suppose this is the arbitrary SFD that has been given to you. This is positive, negative, and you are asked to find what is the moment at this point. You are asked to find the moment at this point. So what you will do is, you will just find the area of this, because this is lying between x equal to 0 and x equal to L, and you will directly quote your answer. Answer will be area of the shaded region. So this becomes important whenever you have to do the reverse analysis. Sometimes they will give you the bending moment, and from that they will ask you to draw the shear force diagram. So by this mathematical relationships, it will be very easy for you to draw the diagram and also get assured whether you have drawn it correctly or not. Now moving on to the next, I will take my problem number 4. So basically the theory that I covered in between will be very much essential to understand the next problems that I will be taking, because I will be taking you a bit a level upper side, because these questions seems to be you may say a very tough question, but after knowing all this theory, you will be able to crack all of them very easily. That's my guarantee, friends. So just go through or recall all the theory part that I said, and also I written in the board. So you go through all these things very carefully. Recall whenever I am speaking it again. You might have seen that I am repeating my concepts again and again. I am repeating the very small things again and again, because these small things will only carry a question in the next slides. And if you are not thorough with that concept, then you will find it difficulty. So all the lectures, all the slides are equally very important, and whatever I am speaking is also equal. It is having the equal weightage, and please properly follow it, and then you will be seeing that it is just flowing like water. This subject is very easy, friends. If you follow the proper rule, and if you follow the proper path, then I am assuring you, in this question you will never leave any question coming in any type of paper, not only in GATE, in BARC, ISRO, in everything. in every paper, you will be seeing that there are problems of strength of material, and you will be able to crack it. Now, again, we are up with a question that we have to draw the shear force diagram and bending moment diagram of this beam that is shown into the figure. So the first task that we always had was to identify the type of beam so that we can assign its various reactions. So as you can see that this is a pinned joint, this is a pinned joint, so it is a hinge, and here there is a roller shown, so it is a roller support. So it is a roller support. So whenever there on the two sides there is a hinge, or in one side there is a hinge and in the other side there is a roller support, then we conclude that beam is a simply supported beam. It is nothing but a simply supported beam. And we also know the fact that the hinges do not resist the bending moment. So what the static equation that we will have in our hand is summation of moment at hinges will be equal to 0. So from this equation itself, we will try to draw our diagram, shear force diagram and bending moment diagram. Now, after showing you this, I just want to draw the free body diagram, and in that I will be finding out the reaction that is being offered by these hinges on the beam. So I will be drawing it again. Now, suppose this is my line diagram of the beam. This is my line diagram of this beam AB, which I have represented it here. There is a couple C. So C, what does it this C represents? C represents a couple, or you can say it is a bending moment. Why bending moment? Why not twisting? Because this couple is acting in the plane which is containing the longitudinal axis. So this is my longitudinal axis, and this couple is contained in that plane only. So we can conclude that this couple is nothing but a bending moment. So I have a bending moment of magnitude C here. So the first task that I have in my hand is to draw the free body diagram. Suppose at this end I draw a reaction which is of magnitude RA, and here I draw RB. Now I am not showing you the horizontal direction in the hinge just because if I show it also, then it's not the problem. So this is RAV, this is RBV, and if this is RAH and this is RBH, so in the horizontal direction, if I apply the static equilibrium force, that is summation of the forces in horizontal direction is 0, then what we get is RAH minus RBH, as it is acting in the leftward direction, should come out to be 0. Now RAH is equal to RBH, and as there are no external force and also there is no any component of the force in the horizontal direction, then I can straight away conclude that it is 0. It is 0. Now I will find how I will going to find the reaction. Now as I cannot apply the summation of force equal to 0 equation, here, because there is no any external load, so I will not be getting any value. But I can write the equation in the variable form only, that RAV plus RBV will be equal to 0. Now again I am writing in a fresh manner, like this was my beam, this is my couple C, this is my RAV. I am omitting the horizontal direction, that this is my RBV. So I have omitted the reaction in the horizontal direction. So this point B is here only. This is my A point. Now the one equation that I was having in my hand is the static equilibrium equation in the vertical direction, that is RAV plus RBV equal to 0. So this is my equation number 1. Now what I will conclude from this relation, that RAV is nothing but minus of RBV. So I am getting an indication that the magnitude of these two forces will be same, but the direction will be opposite because one is having the negative sign. Now I will apply the funda that moment at hinge. I will take any hinge you take, you will be getting the same result. So I am taking it B. So moment at B must be equal to 0. So how I calculate the moment? My section is at B. My section is at B and I am taking all the moments from the left hand side to the section B. Whatever moment that is coming up to the section B, whatever moment is in the left hand side, we will calculate that moment. We will add up that moment, and adding up means with the proper sign. So this RAV is producing a clockwise moment about this point B. And what is the magnitude? And if I suppose the clockwise moment to be positive, then I can write here positive of RAV into L, that is the perpendicular distance. This is the perpendicular distance L, and this couple C is also in clockwise direction. So I will write it here as C is equal to 0. So there are no other moments apart from the moment given by the reaction RAV in the clockwise direction, and the couple, external couple C, that also in the clockwise direction. And what is the bending moment due to this RBV? That will be 0 because this is passing through the point itself. So whenever you are calculating the moment of a force about a point through which it is passing, then automatically the moment about that point of that force is 0. So now I can write it here like this, that RAV is nothing but minus C by L. So RAV is nothing but minus C by L. So what is the equation here that I am having in my hand is RAV is minus of RBV. So I can conclude that RBV is nothing but plus C by L. So as these are having, the magnitude is same, but the directions are opposite. Now I have got my reaction, and now I will be drawing my free body, shear force diagram. So coming on to the next slide, I have shown your shear force diagram, but I will draw it step by step. Like suppose this was my beam, this was my couple, and I have already got the reaction. Now see the direction of the reaction. Here I had assumed RAV in the vertical direction, but I have got a minus sign here. So I will change my direction here, and I will conclude here that my original direction of RAV is in downward direction, and it is C by L. And what is the direction of RBV? As you are already getting plus C by L, so it will be plus C by L only. It will be plus C by L in that direction itself. Now, so I will show you here the reaction again, that it is C by L, and this is also C by L. This is my point A, this is my point B. Now again remember this LURD, that is left upward is positive and right downward is negative. So as this force is acting in the downward direction and it is in left hand side, then it will be a case of negative shear force. So this is my reference line. This is my reference line, and I will be drawing the shear force diagram. So this C by L will be negative, means below this reference line it will be constant because there are no any concentrated point load. I told you that the jump that will come into picture in the shear force diagram will be only because if there are concentrated loads in between the points where we are drawing the shear force diagram. So between these 2 points there is no any concentrated point load. Only what we have is concentrated moment. So shear force has nothing to do with the constant moment present in the between. It is only bothered about the external force, whether it is a point load or uniformly distributed load or uniformly varying load. So it will be constant throughout. It will be constant, and C by L in upward direction it will be like this. So this is the SFD, and the whole diagram is negative, and the magnitude here is minus C by L. And you can see from the figure also it is the same thing. So it is totally negative because it is below this reference line. This was my reference line, and the total shear force diagram is below the reference line only. So now, after drawing the shear force diagram, I will move into the bending moment diagram. So, in the bending moment diagram, I have shown here itself, but I will draw it again step by step so that you don't have any confusion. So here was my couple acting. Sorry, I have shown in a wrong direction. So suppose my couple was acting in the clockwise direction. It was like this, C, and I had got a reaction C by L, and here C by L. Now, mathematically, I will be writing the equation in such a manner that from that equation itself, I will be drawing the bending moment diagram. And from the shear force diagram also, I will show you how I will arrive at the result. So what I will do is, I will take a section plane, because it is just like the method of section which you will find written in many books. So this is the section plane I have taken, that is my XX. And this section is lying, means this section will be lying between 0 to L by 2. So from X belonging to 0 to L by 2, what is the moment of equation that I will be having is, as this force is acting in the downward direction, and it will produce a hogging moment. So I will take a negative sign here, and it will be C by L into X. So again, this is a straight line, and at X equal to L by 2, what will be the magnitude here? It will be minus C by L into L by 2, which is nothing but minus C. So at X equal to L by 2, you have moment as minus C by 2. Now again, I will be drawing whatever the equation that I have written here of the bending moment diagram. So I will be writing here again that from 0, that is from 0 to I will write here L by 2 to X, which is up to L. Means if my section plane is in here, and it is lying in the region of L by 2 to L, and the equation will be here, mx is equal to minus C by Lx, and this couple is acting after L by 2. It is coming into picture, so it will be again producing a hogging moment, it will be a sagging moment as it is in clockwise direction. So it will be plus C, and after that there is no any moment. So this will be the equation. So if my a section is lying at this point, that is my X, that is after the couple, then I will be having this equation. So with this help of two equation, I will be drawing my diagram. So let me rub it again and just remember the results that you have we have calculated right now. So this was my beam, this was my couple, this was my reaction coming into picture. And what was the equation? That was mx equal to minus C by Lx. That was when x is lying between 0 to L by 2. And the second equation that I was having is minus C by L into X plus C when the section plane was after this point of action of couple. Now, so I have drawn a reference line here. Now, this equation up to L by 2 is again a straight line equation because it is a type of y equal to mx equation, and this type of equation always passes through origin, and it makes a slope of m units, which is nothing but the tan theta, that is dy by dx, that is the slope of the line. So this one I will be drawing like this. So as it is a negative sign shown here, so it will be up to L by 2, and at L by 2 what the magnitude that we got earlier, you can see here also the magnitude at L by 2 is it was minus c by 2. So I just represented the point c by 2 here. Now, as this is the equation of a straight line and it is passing through origin, and suppose this is my x equal to 0, this is my origin. So the straight line must pass through this point and it must conclude here, means it must terminate here, because at L by 2 it must be, the value of moment must be minus c by 2. So I am drawing a straight line up to this position. So this is the diagram up to L by 2. Now, after L by 2, you can see that a couple is coming into picture. So this couple is of sagging type, that is of positive bending moment. So this minus c by 2 and this c will be added up and it will come out to be plus c by 2, that is plus c by 2. So how I am getting this plus c by 2? This plus c by 2 is nothing but c minus c by 2, that is plus c by 2. So since this c is the external couple and this c by 2 is the moment that we got from this reaction force. Now again, if you put the value of x equal to L in this equation, as it is valid from L by 2 to L, if you put here L, then what you will get is L will cancel out. So it will be minus c by L into L plus c. So this cancels out and it is 0. So again at this point the moment should be 0. And again this is the equation of a straight line, because x is having a power of 1. So it will be joined by a straight line only. So it will be joined by a straight line. So you can see in this figure itself, this is my negative bending moment, this is my positive bending moment, and we are getting a straight line. So this is degree 1 and this is also a degree 1. So what we did was we wrote the mathematical equation by taking sections in such a way that in the first part the external couple was not covered, and in the second part, covering that external couple, we founded out the reaction, and with the help of that equation we drew our diagram. You can take it, if you find any difficulty in taking sections after the load, you can do one thing is you start taking the equation from right hand side. So it is also very simple, friends. Like here C by L is acting in upward direction. C by L is acting in the upward direction. So what will be the moment equation here? It will be C by L into X. That will be positive because this is a sagging moment. So again it will pass through, the line will pass through the origin. If I take my origin here, if I am taking from right hand side, then it will be here, and at x equal to L by 2, again it will be plus C by 2. As you can see, if you put here x equal to L by 2, I am getting the moment to be C by L into L by 2, which is nothing but C by 2 itself. So you can draw from the right hand side also. So it is very much immaterial if you are drawing the diagram from the left hand side or from the right hand side, you will be arriving at the same result. So this was the bending moment diagram of the beam which was shown as loaded. Coming on to the next part, that is I showed the above problem, the problem that we covered. I have showed it here that this is my loading diagram, this is my SFD, that is shear force diagram, and this is my bending moment diagram. So always whenever you are drawing, whenever you are writing any subjective question, or you are solving a problem where there is many types of load that are acting on the beam, and the drawing is becoming complexer and complexer. So one thing that you can do is always try to draw the shear force diagram and bending moment diagram and the loading diagram one below the other, and do the calculations in one side. So it is always advisable that whenever you are drawing the diagram, why is it so? Because at this point, as you can see, there is a dotted line shown here. So the effect of the diagram here at this point you will be able to visualize very carefully. So what is happening at this point? You can able to see very clearly. So it is always advisable to draw the loading diagram and the shear force and bending moment diagram one below the other. So always try to do and try to do the calculation at the other side. So you will be maintaining a very good neatness, and also your chances of making mistakes will lessen out. Now coming on to the next problem, just is a mathematical expressions that I have taken. I have taken the values so that you will be very much thorough with the concept. Here you can see that it is a type of overhang beam, because there is an extended portion of the beam after one support. So it is a case of overhang beam. So this is the overhang beam. So the first task will be to draw its free body diagram. So as this is A is a hinge joint and B is a roller support, and as after the roller support also a span of 2 meter is out of this means after this hinge. So it is a case of overhang beam. So first of all I will draw the line diagram, and line diagram has been shown here. So how I am getting the 60 and how I am getting the 60 here, I will just show you here itself. Suppose that this is my beam and I have a reaction as RA here, I have a reaction as RB here, and a couple of 120 Newton meter is acting. Now I already told you that we have the static equilibrium equation to find the reaction. So first equation that I will apply is summation of forces in y direction is 0, which will give me the result as RA plus RB is equal to 0. Or I can conclude that RA is nothing but minus of RB. Now what I will be doing is I will be taking the moment about point B. So this is my point A, this is my point B. So moment at B should be equal to 0 because it is a roller support. So taking the clockwise moment to be positive as my convention. So I will be getting plus RA into the distance AB, that is nothing but 2 meter, and about this point this couple is also acting, and this is also acting in clockwise manner. So it will be plus 120, that must account to be 0. So the RA I am getting is minus 120 by 2, that is minus 60. So what will be the value of RB, that is minus of RA, that is plus 60. So what I conclude here, that I am getting a minus sign. It means that whatever direction that I have assumed in the free body diagram is opposite to what I have taken here. So RA will be actually in the downward direction and RB will be in the same direction. So you can directly come into the conclusion the direction of the reaction, because this moment is causing a plus or a clockwise moment. So the reaction should be in such a manner that it produces a anti-clockwise moment. So it will be only possible if in RB, means in B position, the force is acting vertical and at A position it is acting downward. So these two forces will form a couple in the anti-clockwise direction which will resist the moment M. Now I will tell you a shortcut to find this reaction. So just I am deleting here everything. Like this was my beam and this is point A, this is point B, and a couple is at the free end of 120 Newton meter. So we know that the reactions are only preventing this, means they are resisting this moment. So they are producing in a couple in such a manner that they are neutralizing the effect of this 120 Newton meter. And from the calculation we have got here 60 and 60. So without calculating from the moment, one more method is there by which you can directly tell what is the value of the reaction. Like this 120 Newton meter is being supported in the span of AB, which is of length 2 meter. So I will directly divide this 120 by 2. I will get it 60 here, and this direction can be determined by the sense, which must be opposite to the couple, because it has to resist the couple. So what will be the situation here? That this couple will be causing the moment in anti-clockwise direction, and you just divide the moment by the length which is supported in the span. Means this is the span and it is supported by 2 meter distance only. So I will divide it by 2 meter and we will directly get the reaction. So this method will be applicable only when there is only a concentrated moment acting in the beam. So this is the reaction which I was talking about, that 60, this plus 60 upwards and minus 60, they are forming a anti-clockwise moment which is balancing this clockwise moment. So from this diagram itself, we will be able to draw the shear force diagram. So suppose this is my reference line and I have to draw the diagram from this reference line. So as this 60 is acting downward, so from this relation LURD, left upward is positive, so left downward will be negative. So this is my minus 60 here, and it will be constant because there are no any external point load acting in between the point A and B. So it will be a straight line, horizontal line, and again as 60 Newton is at point B, so it will go upward to point B and it will come out to be 0 here. It is A, and after this point B, as there are no any other forces, so my shear force diagram will be this only. So this will be L by 2 length and this is L by 2 length, and this is my shear force diagram. So in the similar manner, if I have shown you to draw the shear force diagram, in the similar manner, after writing equation, we can come out with the bending moment diagram also. So now I will try to draw the bending moment diagram. So I am clearing it off, and suppose this was my beam, and again I am drawing it. This is 120. I am only taking the values. This is 60 and here it is 60. So now if my section is at this position XX, then I will write that my moment equation from 0 to L by 2 will be minus 60x. So why minus sign? Because this is a type of hogging moment that will be coming into picture, because this force will try to tilt the beam in this direction. And remember that Smiley is becoming unhappy. It means that it is a case of negative moment. So this mx will be 0 to x to L by 2. It is minus 60x. So it will be nothing but a straight line. It is a straight line equation. And if in this equation you put x equal to L by 2, so if I put here L by 2, which is nothing but 2 meter, as you can see in the question also, it is 2 meter. So if you put here 2 meter, you will be getting minus 120. So here I have drawn a straight line up to this point. Suppose I name this point as B and A. So up to this B, it is minus 120. So what will be after this point? So after this point, after this 120, you can see that at the free end also there is a moment of 120 meter acting. So at this point B, at this point B, what will be the condition? That this force, just I want to show you that this, as there are no any further forces which will be giving the moment. So in this equation itself, this equation is valid also up to L. This is valid up to L also, because there are no any concentrated load here, but there is a reaction of 60 Newton. So I will write again my equation here like this. Just I am deleting everything. That if I want to make my equation valid, like from 0 to x to L by 2, the equation was simply minus 60x, and from from L by 2 to L, from L by 2 to L, there will be a modification in the equation, that is from x from L by 2 to L, the equation will be minus of 60x, and this 60 is producing, if I take my section here, so this 60 is producing a clockwise moment, so it will be plus 60 into, as this is whole distance is x, and the effect of this moment is from this point. So I will subtract 2 meter from here, x minus 2 meter, and plus 120, that is clockwise moment, should be equal to 0. So if I draw my diagram again, the bending moment diagram, that I had already got a straight line up to this point, that is up to 2 meter, and after that, if I put the value, if I want to get at 3 meter, then I put the value in this expression, and as at 3 meter, this 120 Newton has not come to the picture. So if I put here 3 minus 1 is 2, 3 minus 2 is 1, so it will be plus 60, and this minus 60 into 3 is, minus 180, and this minus 180 plus 60 is minus 120 only, so it will be a straight line only up to the free end, So suppose this was my 2 meter length, and at the 2 meter was the support, this B support was there. So at 2 meter length, I was getting minus 120. This minus 120 will be constant, and at this point it will be 0 at the free end, as there in the free end 120 is acting in the clockwise manner. So minus 120 and plus 120 will yield 0. So this is my effective bending moment diagram. You can see clearly in the picture also, this is the shear force diagram and this is the bending moment diagram. So this was the point up to which the beam was supported, and this was constant up to here, and plus 120 has yielded in 0 result here. So might one of the conclusion that I told you in the theory itself, that at the hinge and at the free end the bending moment must come out to be 0, and we concluded this here also. Now suppose from this bending moment diagram I try to calculate back what is my shear force. So here the slope of bending diagram gives me the shear force. Now this minus 120, what is the slope of this line connecting this one? So the slope of this line is minus 120 by 2 meter, which is minus 60 Newton. So here the shear force will be, suppose this is my reference line, it will be minus 60, and as the slope is constant up to point B, so magnitude will be constant up to point B. Now after point B, the bending moment is remaining constant. It means that a constant bending moment, the slope of a constant is always 0. So the shear force will be 0 only, and you will be getting a diagram like this. So it is minus 60 and the shear force diagram will be like this only. So from the reverse analysis also we can conclude that if you know the bending moment diagram, then we will be able to calculate the shear force diagram. So now from the next topic onwards, just I have told you that we always represent one below the other. So this is my method of representation. I have showed the beam here, I have showed the loading diagram, I have showed the SFD, and this is my BMD. So from the next lecture onwards, I will be starting with the uniformly distributed load, and I will be covering the uniformly variable load, and this will be a bit of a higher level than what we have studied till now, and I hope that you will be enjoying in the later depth classes also. So enjoy your day, have a nice day, thank you.